So I titled my talk "Engineering the Natural and Built Environment from Today's Knowledge and the Future Visions." And it's kind of a, you try to choose these catchy titles, I guess. What I want to say is that the AI methods in an engineering context, of course, should help us to predict the future, to look how our designs, our engineering outcomes will play in the world that is not there. Want to move a little bit back. Why is that so important? I mean, we have significant challenges. I will jump to these. Everybody knows about this, right? But, we face global warming, and we, as I'm a civil engineer by training, as Andre said, we as civil engineers are probably our best customers. So we are not only the ones who need to counteract the global warming by improving our cities, dikes, water retention systems, and so forth, right? But we are also causing most of the CO2 exhaust. And so when we look how we do today, I think it's not sufficient. Let's call it like this. So this is a project that we followed in the Netherlands. It's actually a dike. The Dak Park called, it's in Rotterdam, one of the most densely populated areas in the world, for that matter. And the city of Rotterdam realized in '98 that they need to reinforce that dike, and till they started construction, it was 2010. Right? And then after they started with construction, the project was realized very quickly, but the whole design, conceptualization, everything took just too long. And so the question is really, do we have that time? We need to get much quicker to shape, engineer, and construct our future infrastructure. And I think most of the talks that we saw and the people talked about it provided methods and tools to actually support that. Right? The big question that keeps us busy in Berlin at the Civil Systems Engineering Department is really, how can we make these tools really available for engineering? So how will engineers need to design, engineer, build, and maintain infrastructure? Right? How can they deal with the systemic complexity and the life cycle focus? We need to integrate more and more social and technical innovations in our products, in our civil engineering products. We need to involve specialists, public participation, and do all of this faster. Right? The big question is, this might Andrew Ng, one of the thought leaders, I would say, in international AI thinking, and actually I visited his class when I was at Stanford, and he predicts that AI is the new electricity. So basically, he says that AI will change most industries, like electricity changed most industries, right? And that's all fine, but I think for us engineers, it's of course important to reflect a little bit about how it can actually change engineering and how we engineer products. And as I said, how can we make it much quicker and hopefully more qualitative in that sense. Just some impressions. And so how we look at engineering, like in historical view, and how AI could make an impact there. This is a map I found of the US, and this kind of before they started building the railway to the USA. So probably still one of the biggest engineering feats, right? Building this long railway from east to west, and they didn't know anything, right? So there was no data at all. It was just blank space. So they went a little bit, they surveyed, they engineered on the spot, right, how to continue doing this railway construction work and design work, and then they did it step by step, right? And nowadays, of course, we live in a world where we have like rich information systems that show this is from railway infrastructure. Maybe you would call it already. Nah, I don't want to call it digital twin, right? But we have these available, right? We have 3D models of our cities. We have like very clear and accurate descriptions of our railway lines where we can select objects, and so all that information becomes available, and so we need to make use of it. And so I want to show a little bit of maybe also a personal history, but also a couple of things that I see in that area, right? So how can we make use of the data in the engineering context and use modern AI processes from like what I see as an editor of journals. What I see like kind of trends and tendencies and maybe some things that we need to improve. So when we started working in this area, and I think a lot of people that also gave talks started around the same time, we could book a lot of early successes. And so what we, for example, one of our first studies we did, I think we started with this around 2000, was like detecting road deterioration, right? And so there are databases that show how roads deteriorate, and then we were fusing that data with weather data, and we could build like great models that could predict this with a high accuracy. Yeah, we could write papers about this, and some of these papers are still highly cited. Kind of thinking sometimes a little bit embarrassing, but yeah. And then another example that we did, we could like look. This is a data-driven model we built about asphalt cooling. So when you build a new road, when you pave asphalt, it's very important to understand the temperature of the asphalt during construction, because you need to compact it. And so if you compact the asphalt, of course, when it's still too hot, your compactor will just sink in. If it's too cold, the compactor will just break the surface, right? So, but how do you we measure the asphalt, and when you look at modern asphalt pavers, you measure the asphalt temperature at laydown. But how do you predict it when the compactor goes over? And so we developed a data-driven method with some measurement devices on site that you could install, right, to predict asphalt temperature throughout the construction and asphalt cooling. And we even received a patent for this technology back then. And then completely other example, maybe not so much engineering related, but more operations, right? So we could predict the knock-on delay prediction of the Irish railway network. Okay, it's a very simple network, right? But we took historical data, and so then we could build a predictor that could basically tell us if one train gets delayed tomorrow or in a week, right, what that would mean for all the other trains that follow. And we all know that, right? Whoever drives a train, right? So once one train is delayed, most of the other trains will also delay, and often can end up in these catastrophic days where everybody's stranded on some railway station, right? So just like some arbitrary examples, and I think at that time, probably not the best of the work, others did much better work, but maybe I can talk about these because we did them, but the good overview of the early successes we booked like that. But then I think we kind of lately got a little bit stuck. And I will also show some of our failures now, because nobody ever shows failures, but I will show some of our failures. But then I will also hopefully show some just examples of recent publications. So in the preparation of this talk, I just went basically online, looked for some of our high-end journals, looked what has been published in the latest years, and found examples, right, of things that were published, but they had the same problems that we experienced. And so I think it's very important to reflect as a community about how we can move on, right? So we had these early successes, but now what we see more and more also as an editor of a journal, that we get things like that. So this is one of the things. We tried to develop an early warning system for landslide prediction. Very great data of a slope. This wasn't that slope, right? So there was never a landslide. It's just like a really flashy picture, right? Where we measured the tension of the soil at different depths over time, and we had a great data set, right? And we linked the data set to weather, and we came kind of up with like the predictors that you see here, right? And so actually there were neural networks, right? But this would be the true line that we wanted to predict, and you see that kind of works well, right? The points are quite close to that line, but then we said, okay, great, high accuracy, training worked out, great data set. I think we can install an early warning system, for for that slope. So we started discussing this with the experts. And then when you take a closer look, the experts said, yeah, well, wait a minute, this is kind of dangerous. Right? The predictor looks good, the accuracy is perfect, but you're consistently underestimating the slope, right? And so basically your models are useless for the purpose at hand. While on paper they look good, we never published something about this, maybe we could, right? It's useless, right? So great idea, great method, but for this slope, and I'm not saying for all slopes in the world, for this slope, they're not working. Right? Example just was recently published, right? I'm not talking about the author or something, right? We'll leave that blank. Just an example of many, right? We see these all the time now submitted to our journals, right? So it's like prediction of water inflow in a tunnel, right? So typical machine learning paper in our area, right? So they have a data set, we tried 6 machine learning techniques, and that's from 2001, the publication, right? And then we applied it to, I don't know what 600 data sets means, right? And then they report accuracy of the models were ordered, root mean square error of 4.07, 4.6, right? And so that all sounds great, but that abstract, and if you look at the paper, doesn't speak of anything whether you can actually use the models that they built to predict water inflow, right? Is it biased? Does it overestimate? Does it underestimate? Right? What is the real quality that this model wants to have? Right? And so, just an example, face many of them. Then another example from us. So we were asked by a company. I can't name the company, and I can't show many of the details of this, right? But so this company has like a practice of due diligence asset evaluation. So completely other field, right? And so they have people basically, if somebody wants to buy a new building, they can ask that company, and the people do an inspection, and they do the due diligence and evaluate the asset, but also they tell you what the expected maintenance cost for that building would be in the short term, long term, and so forth, right? In a couple of time spans, right? And so that company thought like maybe 8-9 years ago, it would be great, right? So let's build a database. And what they did basically, they created their own web interface, right, for all the inspectors in Europe. So it's European-wide operation, and so they gave them some standard things that they need to put in, right? And they sat together with them, right, and asked them, so what are you looking for? And and then they put these standards in, right? And then a company and we worked together and said, now after 10 years of data, we should be able to predict something like that, right? So this is, after all, this is the things that the items that our inspectors say that they look for, and that's important, right? And then, as I said, I can't show much of it, but in the end, it was a big failure because this is just like some plots, some box plots of the data distributed according to, the cost per area, and then different types of offices, and the cost in the long run, the cost in the mid run, and the cost in the short run. And so we tried algorithms and tried to think, but in the end, it turned out the model could never predict better than just taking the area. Right. Interesting detail, and we never got further with this. But they had also a field for free descriptions, and we did some initial text mining of the free descriptions, and the results look much more promising than taking all the standard items. So looking at just a recent presentation, right? So sidewall displacement, 210 data sets. I still don't know what they mean with data sets, including 12 useful parameters. were gathered from 10 underground cavern projects, right? And then 74% and 26. Okay, you can do it like this. And then, yeah, great model. Correlation coefficient of 0.9998, root mean square error of 0.002059, and they account for variance of 99.98181. So oh, kind of, then we should have published our earlier study as well. So they tried long short-term memory, deep neural networks, k-nearest neighbors, Gaussian process regression, support vector regression, and decision tree. So it's like, okay, probably a little bit overkill for what you're doing. So something we also see, so we see that many models are built that have a good accuracy, but they're not fit for the purpose. Now, this is an example where, a model was built that's probably very, very fit for the purpose, but much too complex. Could have been probably much easier. All right. Other example, this is a collaboration that we did with Deutsche Bahn and the Bundesanstalt für Materialforschung. And this is really automated damage detection for railway tracks. This is kind of like figures you get from the Deutsche Bahn testing trends. So this is Curry eddy measurement, and then you get like pixels, and these pixels have like different things in them. Green, to something happens, right? And so what you have, and I'm sorry that's in German, right? So you have like boreholes, right? Then you have Schienenstöße, where two pieces of rail meet each other, right? And then you have like some signals, right? Signals at the bottom, signals at the top, right? And these signals might point towards damages and defects in the right. And so we also started working on this, and when you look at this data, right? So data is of course highly unbalanced. So when you look, we had, and this is just a very short track. I think it's 1 kilometer or 2 kilometers. And so the Deutsche Bahn has trains running, and they go per day 80 kilometers. So, just like a very short thing, but you already see that a lot of cases, which you see here with the zeros in the confusion matrix, nothing happens, right? And only, in these instances, you kind of have like, and this is for predicting failures at the top of the rail, right? They are not boreholes and so forth, right? And, kind of have this, right? And then, of course, this model has a really high accuracy. Right? And you might think, okay, this is logic, right? So you can't use that model though, because the specificity, sensitivity, what you want to know, right? So 75 of the defects were actually not detected, right? It's useless. So you can't really, again, model is actually not fit for the case, right? Then, yeah, so another model, and so this is, again, just an abstract, or, the performance of the model is validated with a mean average position of 85.37, the proposed output of the system. So this is about sewer pipe defect detection, right? Includes labeled CCTV videos, frames that contain defects and associated. The labeled video can serve as a benchmark, right? So is that fit for purpose? Why do they actually, when they want to detect defects, why do they only report the mean average position? And what's with the sensitivity? What's with the specificity? What's more important in this case? So we actually see also a lot of these publications crop up, and they make it into these are all recent publications. So maybe I don't even want to blame people, but I think we need to be much more reflective of what we're doing at the moment, guys. And then last example I brought, this was a thing we did on the Safe10T project together with Network Rail in the UK. Was the pictures are quite bad, but this is probably what you get in resolution from historical data of their inspection. So this was masonry inspection. And so they gave us, they had pictures, and they said, the inspectors went out on site and they took the pictures, and then they had reports, and they said, here's water regress, here's falling. And then, of course, they're like, we put some pictures into this data set where there are no faults, right? And then once you know what it is, right, you can use now old school techniques. You don't need like comminuted neural networks or something, but you just use standard filters, right, and can identify the defects quite easily. But the problem here is, of course, when you have pictures like that and they are in a report, how do you label them? Who says that it's a defect, right? So, I mean, I'm not an expert in masonry or something, right? But somebody said this is water ingress. Who said that, right? So who's labeling your data sets? That, you get a data set that you can use to train your model that actually really describes these defects. Right? And so this is also something we see quite often in papers that are submitted or published nowadays, right? So this is from another masonry paper, great masonry paper, right? And so this is from the paper, right? The aim of this study is to examine deep learning techniques for crack detection on images from masonry walls. A data set with photos from masonry structures is produced, containing complex backgrounds and various crack types and sizes, right? So, I mean, this is the abstract. Maybe you have something in the research method, right? How that data set is produced, but they didn't say anything who labeled it, who decided what's a crack, what's a defect, right? Of course, the problem goes much further because, you know, that's also something that the Deutsche Bahn example, or here, like even if there's a little crack, is it, you know, something that's important for the whole system level, right? So just like 4 pitfalls that we stumbled upon more often as we went on, and, you know, that we see also occurring quite often. So the big question, I think, to move forward that we need to ask ourselves as engineers, and probably that's our main contribution we can add to the field. And you know, we need to work with the computer scientists, right? How do we really formalize engineering knowledge in this? So what are good performance metrics, right? That somebody would, then engineer could confidently use your model, right? How well does something need to perform? What are damages at all, right? What are defects? How do they affect our whole system, right? So we usually can identify small defects, but is it bad for the system? Do we need to do something? Do we need to fix it, right? And then, of course, you know, how to integrate these data-driven models in the engineering work are probably very important, at least in my view, research questions, how we need to move forward and what we can contribute as engineers, right? Want to close this, right? So this was kind of state of the art, and I'm pretty sure a lot of people do the right things already, right? But some trends I see, or some things I see, which we also need to start thinking of. Haven't seen much work in that area, in these areas, but I think it will be really important to certainly improve, right? And so one of the stuff that you see from other domains coming in, this is an example from chemical engineering, right? Where they implemented the how gold behaves and how gold clusters, right? I have no clue about this, right? But was kind of an interesting paper, right? How they could integrate that knowledge, their knowledge about how a material behaves, into, you know, how they train the algorithm into the learning process. I think that is for us something with huge potential, right? We have rich engineering knowledge. We also have very good, we don't, you know, these are all data-driven models, but we have a lot of analytical models, like theoretical models, right? That we might be able to integrate with the learning process to really improve and make use of the AI technologies. The second thing that I think will be very important in the future is how do we verify models, especially when we're civil engineers. So a lot of our things, also a lot of the things I showed of the examples are very safety critical. So, you know, how can we safeguard that our models perform well? Also, when you send them some kind of, like, you know, input parameters that wouldn't play so well, right? Still need to make sure, right? And so probably need to look a lot about model verification and adversarial attacks. So these are just like 2 standard works in adversarial, right? So the Goodfellow is a classic, right? They had a panda picture and they overlay some noise on the panda picture, right? Just 0.07, very small, and all of a sudden the panda was like that was predicted with 57.7% confidence, was predicted with 99.3% confidence, but not as a panda, but as a given. Safety critical. So this is an example of ICOL very well, who like said, wait a minute, you know, you have a lot of graffiti on stop signs, autonomous driving and so forth, right? So when you change the format of a stop sign, and they could develop this example that you see on the right-hand side, that was then actually predicted as a 45 miles per hour sign, that, you know, is probably severe failure that would happen then, right? And so I think we need to start thinking a lot about this as well. And then one thing, and that's my transition to the talk that's going to follow after me, Philip Geyer, is explainable AI, right? So how can we explain these models to the public to all stakeholders, to other engineers and so forth. And that was my little talk. Thanks for the attention. I hope it was a little bit interesting.